There's a new space telescope in town that will map the geometry of the dark universe. ESA's Euclid telescope launched on July 1st, 2023 from Cape Canaveral, Florida, aboard a Falcon 9 launcher. It was going to launch on a Soyuz from ESA's launch site in Kourou, but then Russia invaded Ukraine, so no more launch contracts for you. For the next 30 days, Euclid cruised to the Sun-Earth L2 point where JWST and Gaia currently orbit. And sure, there's actually the Russian Spectra RG spacecraft that carries Germany's eRosita telescope, but then Russia invaded Ukraine, so Germany put eRosita into safe mode in response, so no high-energy astrophysics for you. After Euclid was completely focused, ESA released these sets of images from its science instruments. These instruments will be used to measure the positions, shapes, and redshifts of billions of galaxies as far as 10 billion light-years away. The result will be the largest and most accurate 3D map of the universe ever created. It will reveal the distribution and density of matter in the universe, 95% of which is in the form of dark matter. The geometry of the universe depends on the density of the matter within it. Too low, and the universe is open, like a saddle. Too high, and the universe is closed, like a sphere. But if the density is just exactly perfect, the universe is flat, like a piece of paper. Knowing the shape of the universe is more than just an intellectual curiosity. It tells us whether the universe is finite or infinite, and whether it will eventually collapse or continue to expand forever. Since the nature and ultimate fate of the universe hang on its shape, it's fitting that this mission was named after Euclid of Alexandria, who created the field of geometry in 300 BC. So today we're going to talk about Euclid's mission and what we can expect to learn from it. Euclid is a survey mission, so it's using a relatively small 1.2 meter telescope. Now that's only half Hubble's diameter and less than 1/5 of JWST's diameter, but Euclid is an entirely different telescope for an entirely different purpose. HST and JWST each look at a tiny patch of the sky to make detailed observations, and anyone can apply to use them. Euclid, on the other hand, goes wide and shallow. It takes one image of the sky after another and sends them back. There's no guest observer program, so it won't be taking any requests. But at the end of its mission, it will have surveyed something like 15,000 square degrees of the sky. That's a lot of sky. But not the whole sky, because it ultimately is trying to image distant galaxies. So it has to avoid the Milky Way because it blocks our view of them. But Euclid must also avoid the plane of the solar system as well. And that's because it's surrounded by dust left over from its formation. And that dust reflects sunlight back towards us and creates a faint glow called zodiacal light that can be seen under really dark skies. Otherwise, Euclid will image about a third of the entire sky. It does this by taking a series of images that cover about 0.75 square degrees every hour. That's about 3 times the area of the full moon. And that's a lot of sky to cover in just 1 hour. But even at that rate, it will take Euclid about 6 years to complete its entire survey. Now, Euclid is hardly the first deep galactic survey. The Sloan Digital Sky Survey has been operating since the late 1990s and has mapped the large-scale structure of a huge chunk of the universe. But SDSS is limited to the northern hemisphere because the Sloan telescope is located in Arizona. And besides, the science Euclid is trying to do requires being able to make precise images of distant galaxies. Without the atmosphere to distort its vision, Euclid gets a pristine look at the cosmos. Not only that, but space allows Euclid to go relatively deep for a survey. Its visible light camera reaches magnitudes as low as 26.2. For comparison, the Andromeda galaxy is magnitude 3.4, so Euclid will be able to detect galaxies that are 1.3 billion times fainter than Andromeda. Each patch of the sky will be observed only once as part of Euclid's wide-field survey. However, for a much smaller area, Euclid will observe up to 50 times longer and produce extremely deep images. Euclid's deep survey covers around 53 square degrees in total. And that's not much compared to its wide survey, but that's still more area of the sky than observed by HST in the last 30 years. After it was focused, the Euclid team released these initial images taken with its two science instruments. Now, these are engineering images, so they haven't been cleaned up for science. They're just to evaluate the focus, much like the way JWST's first images were for evaluation purposes as well. The Visible Light Instrument, or VIS, is a 609 megapixel imager that consists of 36 detectors in a 6x6 array. At right is a zoom in on one of the detectors. Notice that stars produce 6 diffraction spikes, and that's because Euclid's secondary mirror is supported by 3 struts. This is similar to the way JWST produces multiple spikes. In addition to the stars, VIS shows a few galaxies and a star cluster. However, there are artifacts all over this image. The streaks are caused by cosmic rays striking the detector. There's also what appears to be some ghost donuts that's actually light from nearby stars reflecting around the telescope's internal optics. Artifacts like these will be cleaned up by Euclid's data reduction pipeline before they get used for science. The near-infrared spectrometer and photometer image is produced by a 4x4 array of near-infrared detectors. NISP also shows fewer cosmic rays compared to VIS, and that's because its active layers are thinner, so the probability of a cosmic ray actually leaving an impression on the detector is much less. There are, however, some additional artifacts, like this odd pear-shaped feature, as well as some curved streaks. These are coming from pixels that are either more sensitive or have charges that build up even in the absence of photons. In addition to imaging, NISP can also take spectra of everything in its field of view. So instead of images, you get these long streaks of light going from the shortest wavelengths at the top to the longest at the bottom. These are the first-order spectra of each object. However, each spectrum comes with its own snowman or peanut. These are the 0th order spectra, which in this case is just a less spread out spectrum of the same object. There's also a number of single faint points without any spectra that are probably head-on cosmic ray hits, or maybe they're caused by something in the pixels themselves. In any event, all of these artifacts will get removed as part of the data reduction pipeline. During its survey, Euclid will image distant galaxies so it can map out dark matter in the universe. Of course, dark matter is invisible, but you can still detect it by looking for gravitational lensing. And this is a consequence of general relativity, which says that matter distorts spacetime. So any light from a background galaxy passing through a foreground clump of matter will get distorted as well. The strongest lensing comes when galaxy clusters with large amounts of matter distort background galaxies into elongated shapes. It takes a lot of matter to produce these distortions. So the foreground galaxies act like tracers of the invisible dark matter that dominates the cluster. But the less concentrated dark matter between clusters distorts background galaxies as well, only just not so much. So it can only introduce a slight distortion from the galaxy's original shape. This is why you need to go to space. Ground-based surveys will always have to contend with distortions from Earth's atmosphere that will overwhelm any distortion due to dark matter. But even from space, each galaxy has its own unique shape and orientation. So how can we know that an individual galaxy is getting distorted by dark matter? Well, the answer is simple. You can't. But what you can do is look at galaxies that are close together in the sky and compare their elongations and orientations. If there were no dark matter present, then you'd expect that if you average together all of their shapes, their different elongations and orientations should cancel each other out, and the average shape would just be a circle. But if there's sufficient amount of dark matter in the foreground, you'd expect to see a slight net elongation at a slight net orientation. And that tells you where the dark matter lies between you and those galaxies. If you then subtract away the light, you effectively have mapped the unseen dark matter in the field. And if you know the redshifts of the galaxies that you're measuring, you can build up a 3D map of the dark matter between you and the most distant galaxies. Obviously, this is an oversimplification. It takes a lot of statistical analysis to tease out the correlations in the galaxy shapes, And you have to account for other things like tidal distortions between galaxies that are physically close to each other. But by repeating these measurements across the sky, you eventually end up with a map of the dark matter distribution in about 1/3 of the universe. So, what can we expect to learn? Well, with a map this deep, it becomes possible to determine things like whether dark matter is smoothly distributed throughout the universe, or if it's clumpy. And if so, how clumpy is it? Knowing how clumpy dark matter was in the early universe will have implications for understanding how the first stars and galaxies formed. Then you can compare the clumpiness of matter at different redshifts to see how it changed over time as the universe expanded. And that will tell you something about how the expansion rate of the universe changed over time as well. You see, if the expansion rate is strong at a given epoch, then dark matter is going to have less time to clump and its distribution will be relatively smooth. But if the expansion was weak, then there's going to be more clumping. From the Planck satellite's measurement of the cosmic microwave background, we know the universe started out expanding rapidly. Then follow-up surveys at lower redshifts indicate the universe slowed down before speeding up again at around redshift 0.6. But for now, we only have a rough idea of the overall trend. Since Euclid is going to observe such a large chunk of the universe with more galaxies over a large range of redshifts, we'll be able to fill in the gaps on this plot and better understand this trend more precisely. And that means we'll be able to better understand the dark energy that's accelerating the expansion rate of the universe, which, not for nothing, is about 68% of the universe's makeup nowadays, so it's important we understand it better. When you know things like the density of the universe and how it changed and how the rate of expansion changed over time, then you can investigate how old the universe really is, whether it's closed, open, or really flat, and whether it will keep expanding forever or if it'll eventually stop and collapse into a big crunch. But cosmology isn't the only science Euclid will enable. Large surveys cast a wide net, so they pick up on data points that aren't relevant to the core mission but are going to be useful in other areas. For example, the Euclid team expects to detect at least 100,000 solar system bodies like asteroids, comets, and Kuiper Belt objects. It will likely detect exoplanets as they pass in front of background stars, magnifying their light in microlensing events. Euclid's deep surveys will probably reveal up to thousands of supernovae at distant galaxies out to redshifts of 2. Type 1a supernovae in particular can be used to measure the rate of expansion in the universe, while core collapse type 2 supernovae help reveal the history of star formation in the young universe. Thanks to Euclid's wide field of view, it will map out large areas surrounding nearby galaxies that Hubble and Webb can only image parts of because of their narrow fields. There's a lot for us to learn, but we're going to have to be patient. After its 3-month commissioning is over, Euclid then begins its 6-year main survey. There's going to be 3 data releases along the way, with the first around 2.5 years after launch. So we're probably looking at around December of 2025. Then the second release comes 2 years after that, and the final release at the end of 2030. About a year ahead of each release are going to be quality releases of selected data, while the rest is getting prepared for science. And that will give scientists a better idea of what kind of data to be expected and to get ready to analyze those data releases when they come out. If everything goes well with the mission and there's propellant remaining, then they may be able to extend for even longer. And that'll be really cool because Euclid will overlap with the Rubin Observatory, which will be making its own wide and deep survey of the southern sky. And that'll allow for an independent check of some of Euclid's measurements. And Euclid's mission may even overlap with the Nancy Roman Space Telescope, which is scheduled to launch in the late 2020s. Like Euclid, Roman is designed to study cosmic acceleration, but it takes a very different approach. Whereas Euclid will create a 15,000 square degree map of the universe, Roman will only cover 2,000 square degrees, but it'll probe much deeper than Euclid, reaching as far back as 2 billion years after the Big Bang. Euclid will likely observe the entire area of the sky that Roman will scan, And that means Roman's more sensitive and precise data will then be used to apply corrections to Euclid's and extend those corrections over Euclid's much larger area. Between Euclid, Rubin, and Roman, we're about to learn a great deal more about the universe, from its very beginnings to possibly its ultimate fate. My thanks as always to my Patreon supporters for helping to keep Launchpad Astronomy going, and I'd like to thank Kenneth Stapleton for becoming my newest supporter. Until next time, stay curious, my friend.